Key homomorphic computations for RAM, fully succinct randomized encodings and more by Damiano Abram, Giulio Malavolta, and Lawrence Roy, and Damiano is giving a talk.
Test. Perfect. So, hi everybody, my name is Damiano, and today I will tell you about this work I wrote in collaboration with Giulio Malavolta and Lawrence Roy. So our story starts at Eurocrypt 2014 with the work of Bonnet, Gentry, Gorbunov, and many other authors you see on the slide. And yeah, in that paper, essentially, they build these lattice-based key homomorphic encodings that from now on I will refer to as BGG+. So if you're new to this area, you essentially need to know that this is essentially a tool that allows us to authenticate computation in a similar way to how FHC allows you to encrypt computation. So formally, an encoding of some value x is some authentication string C that is generated under a pair SM, where S is a secret key, so something that remains private, whereas M is a public key, something known to everybody. And yeah, the encodings of Bonnet et al. Have very nice homomorphic properties that are illustrated in the following example. So suppose we have two parties, Alice and Bob. Alice holds a value x that is going to be authenticated, whereas Bob holds some random secret key S. And here we are assuming that Bob at some point sent an authentication of x to Alice, which is generated under the pair SM, where S is the secret key only known to Bob, whereas M is some publicly known to everybody. And yeah, in the construction of Bonnet et al., we can homomorphically evaluate any function f on all this material. And in particular, that means that Alice is able to derive an authentication on f of x that uses the same secret key S chosen by Bob. So nothing changed, and Alice does not know this S. So the public key, however, switches from M to MF, where MF is something that everybody can compute by homomorphically applying F on the original public key M. So it's a bit complex, but to summarize what's happening here is that given an authentication of X, you can get an authentication of F of X that uses the same secret key S, even if we do not know it, and the public key switches from M to MF, where MF is obtained by applying F on the original public key. And yeah, in the original work of Bonnet et al., both parties had to perform computations proportional to the circuit size of the function f we are evaluating. And that is inherited by all the applications of this tool. And there are many of them. Like here are those that I could remember, but probably there are many others. These BGC plus encodings were used for attribute-based decryption, laconic function evaluations, variants of constraints PRF, homomorphic signatures, trapdoor hashing. And yeah, in all of these primitives, typically there is a party that homomorphically evaluates some function f on some encodings, and that party needs to perform computation proportional to the circuit size of the function. And yeah, in the work I'm presenting today, we managed to improve this. Like we modified encoding so that the total computation of both Alice and Bob scales proportionally to the run complexity of the function f. And that means that this improvement is inherited by all the application, including those that I'm not aware of. Now, the computation of the evaluator scales proportionally to the run complexity of the function. There is also another interesting feature of our improved encodings, namely the space complexity. Indeed, only Alice's size scales proportionally to the original space complexity of the function f, whereas Bob's computation for the homomorphic evaluation of the function on the public key has constant space complexity, a polynomial in the security parameter. And this is important for our main application, the one you see on the title of the paper, namely succinct randomized encodings. So if you don't know what this is, essentially it's a primitive that you would use to securely delegate computations. You have a function f and some private input x, and this function is complicated enough that you don't have resources to evaluate it. So what you're going to use is these succinct randomized encodings. You generate some string in time much smaller than the evaluation of the function. You send it to some delegated party that will derive f of x without learning anything else. And yeah, Previously, this primitive was known only from I/O. Like it's only in the last 2 years that we started figuring out how to build it from other assumptions. And notably, there is this work by Nir Bitansky and Ratchet Garg at Eurocrypt this year, where they built these succinct randomized encodings with complexity t to the epsilon. Epsilon is any constant you want. T is the original complexity of the function f. And yeah, they built this by essentially recursively nesting these BGG plus encodings. And due to space complexity blowing up, like they could do it only a constant number of recursive steps. But now we do not longer have the issue of space complexity. We can push the recursion even further. And we managed to obtain essentially succinct randomized encodings with polylogarithmic in T complexity. So this is all I will say about these applications of our tool. I think that really this is not the most important point. The most important contribution is actually the techniques. So my hope for today is to give a sketch of how they work, and hopefully you go home with at least an intuition of what's happening. So essentially, we introduced these new encodings we call compressed encodings that essentially authenticate the whole RAM memory, this huge vector X. And the compressed encoding, of course, is small. Moreover, it has very nice homomorphic properties, meaning that we can homomorphically perform read and write operations. And both of these take polylogarithmic time in the size of the memory. So suppose you want to read the ith entry of the database. Well, you can homomorphically read from the compressed encoding and end up with the BGG plus encoding of the ith entry xi. And yeah, this is an encoding like the one of Eurocrypt 2014. So at that point, you can homomorphically perform the usual computations. And so at some point, we may have changed these to some value xi prime that we want to write back into the memory. So we need to update the compressed encodings. Once again, we can perform this homomorphically in time polylogarithmic in the size of the whole database. And yeah, the key tool is actually to build these compressed encodings is a trick we published as Stock this year. So if you want to understand the math underlying this construction, I really recommend you check that paper. That is where the magic happens, let's say. And yeah, there we build this particular SAS-like hash function, therefore a linear hash function, that can be homomorphically inverted on encoding of digest, as long as we know a preimage of this digest, specifically. Suppose we have an SM encoding of some digest D, for which we know a preimage, therefore a small string. Then we can homomorphically expand this to an encoding of the preimage X. So the secret key here remains the same. However, in order to perform this operation, we need some auxiliary material, namely this big blue square on the left, which essentially consists of a circular encryption of the secret key S. Now, this blue square is actually huge. It's much bigger than the input size of the hash function. However, and this sounds like it defeats the purpose of compressing the encodings. However, this blue square has still a very nice property, namely that its value is independent of X and the digest. So this blue square is reusable. We will amortize its cost over many execution of the hash function, specifically. Now, imagine we have this big RAM memory, like this huge vector X. We instantiate the SAS-like hash function so that the input size is much smaller than the whole memory. And that means that the blue square now, it's small because its size depends only on the input size of the SAS-like hash function. And yeah, what we will do is we will hash this RAM memory using a Merkle tree, where the basic hash function is the SAS-like, and we will reuse this blue square for the whole execution. Okay, so the compressed encodings are as follows. They're made of two parts. The blue square that, as I said, is small, is the circular encryption of the secret key S. The other part is a BGG plus encoding of the Merkle digest T, which is small. And yeah, my claim is now we can perform read and write operation homomorphically in time polylogarithmic in the size of the memory. Let's start from the read operation. Suppose we want to read the ith entry and we hold some BGG plus encoding of the bits of I. We start from the root. Now we have a BGG plus encoding of a digest. We can assume we know also the preimage for the SIS like hash. And we have the auxiliary information, the circular encryption of S. So we can expand this encoding at the root to an encoding of the preimage. But now the preimage is the concatenation of two other SIS like a digest. We are only interested in one of them, the one on our path to the ith leaf. So we can use the homomorphic properties of these BGG plus encodings together with the encoding of the bits of I to select for the one on the right, like in this example. Now we are back to the initial states because we have an encoding of the digest. We can assume we have a preimage to the digest. And we have again, like the auxiliary material, the circular encryption of S that always remains the same. And so we can go up again, an encoding of the concatenation of two digests. I select for the one on the left using the BGG plus encoding of the bits of I, and I repeat until I reach the leaf, and I have a BGG plus encoding of xi. Total computation, polylogarithmic in the size of the memory because we need to do an expansion for each layer of the tree. Okay, now we have the BGG plus encoding of xi. We can do all our homomorphic computations we want on this. And we can imagine that at some point this turn into a BGG plus encoding of some other value xi prime that we want to write back into the memory. How do we perform this operation? Well, we need to update the compressed encodings. One part is already okay, like it's the circular encryption of S. S remains the same, so we don't need to change that. We need to change the encoding of the digest D that, of course, has to be updated because one entry changes, the Merkle digest changes. And how do we do that? Well, we just need to homomorphically reevaluate the digest on the path that go from the ith leaf to the root. So we start from the top, we have a BGG encoding of xi, we have a BGG encoding of the bits of I, and we have a BGG encoding of all the siblings of this entry, because we had them from the reading procedure when we expanded these hashes. So we can recompute the hash at the top layer. Now we have a BGG plus encoding of the updated digest one layer down. And then we repeat, because the next hash we need to compute is the concatenation of the purple thing you see one layer down with what comes from the right. But we already have a BGG plus encoding of that thing because we obtained it from the expansion procedure earlier. And so, yeah, we repeat again and again until we end up with the BGG plus encoding of the updated digest D prime. Total computation, again, polylogarithmic in the size of the memory, because we just need to perform a homomorphic evaluation of the SIS like hash function per layer of the tree. Yeah, so to summarize, how do we perform RAM operations? So we start from the empty memory, like a huge vector of exponential size 2 to the lambda, where all the entries are 0. We compute a compressed encoding of these, and we can do it efficiently because our Merkle tree is linear because the basic hash function is SIS-like. So the hash of 0 is 0. So it's quick to compute. At that point, we perform read and write operations. For read operation, we just need to expand the encoding of the digest along the path towards the entry we want to read. To perform write operation, we just need to homomorphically recompute the digest on the path from the entry we are updating to the root. The last thing I wanted to say is assumptions, because we couldn't build this just from standard LWE. And the issue is this circular encryption of the secret key S, the blue square. Essentially, this consists of these t-square terms, Cij. T is a parameter that essentially denotes how much the SIS-like hash function is compressing, but you should view it as square the dimension of the lattice, more or less. And yeah, these CIJ terms are made as follows. So there is some public material consisting of two T matrices. The first T are sampled uniformly at random and are fat, whereas the last T are thin matrices that are low norm. And they are chosen in a way that I can multiply any of these AI by any of these BJs. And yeah, the term Cij is going to be what you see on the slide. So there is the secret key S multiplied by AI times Bj. You add noise, and then there is this last term that is the one introducing the circularity. There is the chronicle delta, delta j meaning zero almost always, except when I is equal to j. In that case, we have one. And then we have S transpose times G, where G is the gadget matrix. If you know lattices, you've already seen that. If you don't know lattices, this is just a fixed metric, so don't worry. And yeah, it turns out that this part on the left in the blue rectangle can be proved to be random under LWE. Like essentially you have a hybrid in which you use LWE with respect to the matrices AI and the secret S. And then the second hybrid uses the new secret and the matrices B. However, there is the circularity because we have S also on the right side. And that is why we had to make a new assumption. We call it decomposed LWE. Essentially, it just says that all these Cij look random. And even if we didn't manage to prove any connection to a WE, actually we believe that this is strictly stronger, we managed to prove that this is an assumption weaker than succinct LWE that was introduced by Hoeteck at crypto last year. And so that's it. So here is a summary of the results, and I'm happy to answer any questions.
Thank you, Damiano. We have time for questions.
This circular security and the usual circular security, let's say correctly.
We don't know. Like this one seems much more structured. Like if you take a GSW encryption of S, here instead, like you can move. I don't know. Wait a second. Maybe I should go back one slide. Does it work? Yeah, essentially the term at the very end, like this S transpose times G, can be moved in as part of the matrix. So I mean, you can, but like then you have a structural matrix because it's of the form AI times Bj plus delta HIG.
It seems so morally different in the sense that you know the FHE circular security assumptions, they are all the same. It turns out the GSW and BGB and so forth, they are more or less the same, but they encrypt quadratic functions.
Yeah, and here instead everything is very linear. Like that is the tricky thing. Like I don't know, like if it is a positive thing or a negative. Positive in the sense that you have the math to analyze what is going on here. Negative, well, like it could be that that math breaks the assumption, but yeah.
Do we have any other questions for Damiano? Yeah.
Thank you for your presentation. So my question is like about the security of this hash construction used here. So like this hash computation is like is similar to the SIS based.
Yeah, it's essentially SIS with I don't know, like you put like in block form, like the hash key is actually low norm, but like essentially it's SIS.
So like I think this is not like as strong as like for example SHA-2 and so on. So like could you explain like intuitively like why like using such like a SIS based hash function is like secure enough to like construct a kind of like a kind of like a macro tree to like get the digest of the like memories?
And like SIS is a very standard assumption.
Yeah.
Does it like so? You're good with implementing like Merkle trees with SIS for sure. Like here, the novelty is this circular encryption of S. But if it wasn't for that, we have everything from LWE. Like so, yeah. I don't know if it's. I don't know.
Thank you.
Yeah.
Or maybe we can take further questions offline. All right, let's thank Damiano again.